Now we want to start to build on the tools that we have, and therefore we want to utilize the tools that are available to us in the signal processing context. So first let us look at some basic operations on discrete time signals. So basic operations on discrete time signals. Okay, the first operation that we would like to quantify or to introduce is the notion of a delay that we can introduce in the signal. So if you have a signal x of n, a discrete time signal, we can talk about another signal y of n, which is equal to x of n minus n naught, where n naught is also an integer. N naught is an integer, and n itself is greater than minus infinity to infinity. Basically, it's a signal that goes from infinity to infinity. So basically, you have a signal that is x of n. Let us take one example. Okay, a very simple sequence. At time n equal to 0, it has got a height of 5. At time n equal to 1, it is 4, 3, 2, 1, and then it is 0 after that. It is 0 before time t equal to 0. Okay, so this is the sequence that we have. This is x of n. Okay, write down, this is 0, 1, 2, 3, 4, 5, minus 1 and so on. The height is given by 5, 4, 3, 2, 1 and then 0 on. So if I were to ask you to write down this sequence using the notation that we have already introduced, it will be x of n open bracket 0, 0 or many zeros, and then comes 5, 4, 3, 2, 1 and then zeros after that. Okay, this would be the sequence, and the origin is corresponding to the sample equal to 5. So basically, whether you draw it graphically or you write it in the form of a sequence, both are one and the same. So what I would like to do is request you to form a small table where we write down the value of n, start from minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7. So minus 2 to minus 7, you form your table. Okay, the first row is x of n. You have 0, 0. At time n equal to 0, it is 5, 4, 3, 2, 1. 5, 4, 3, 2, 1, and then sample number, this will be 0, 0, 0. Those are zeros. Okay. Now, y of n is equal to x of n minus 1. Okay. That means at time n equal to 0, y of 0 is equal to x of minus 1. So, y of 0 is equal to x of minus 1. So, draw a little arrow and this becomes your signal, x of minus 1. Y of 1 is x of 0. So, basically you will get a sequence which starts at 0, 5, 4, 3, 2, 1, 0, 0, and it will be 0 before that. So, this is what we call as a delay. It is a shift in the time axis. So, what was originally at 0 now moved to the sample value equal to 1. So, this is what we call as a shift operation. Now, you could also shift it in the other direction. So, we can go ahead and write down the sequence y of n equal to x of n plus 1. Okay. In this case, y of 0 will be equal to x of 1. Y of 0 will be equal to x of 1, which is the value equal to 4. Y of 1 will be equal to x of 2. 4, 3, 2, 1. What happened to the 5? That goes to minus 1. Y of minus 1 is equal to x of 0. So, this becomes 5, and then there is 0 and then 0, 0, 0. Okay. Now, it is also very helpful for us to understand how these shifts occur when you write it in the form of a sequence. Okay, when you write it in the form of a sequence, x of n is equal to 0, 0, 0, we already wrote it, then comes 5, 4, 3, 2, 1, 0, 0, 0. This is x of n, the origin is here. For x of y of n is equal to x of n minus 1, you take this entire sequence. Okay, we will paste it here. So, this is y of n. This is y of n. We will make it all red so that it corresponds to the signal on the left side. This is y of n. Origin has moved to this point. So, this is now the origin. This is y of 0. Everything has moved to the right. So, this is a shift operation. If you call this as y1 of n, they call this y1 of n, they call this as y2 of n, you take the same signal and write it here, blue color. Okay, this is y2 of n. y2 of n, where did the origin move? The origin moved to the value sample equal to 4. So, basically the same sample moved left or moved right. So, if I were to ask you to sketch this, you should be able to sketch it. Edit, copy, paste. Okay, so now we want to sketch y of n. Okay, y of n is like this. The origin, this axis will now be moved like this. Okay, let me do this like this. Right. So, this is what the y of n looks like. The sample at time 0 is 0, at time 1 is 5, then 4 and so on. So, you can then go ahead and look at how the shift operation is working. Okay. Now, I would like you to look at a very simple but important operation, the unit sample. If I ask you to draw the unit sample, quickly sketch that. Time n equal to 0, you have a sample of value equal to 1. So, this is delta of n. Okay. Now, I want you to sketch delta of n minus 1. N minus 1 is, this is 0, 1, 2, whatever was at 0 now will move to 1. So, this is delta of n minus 1. Okay, and delta of n plus 2, that means it has been advanced by 2 units of time. Sketch delta of n plus 2. So, here is 0, minus 1, minus 2, 0, sorry, 1, 2, 1, 2 and so on. The unit sample is now sitting at the minus 2. This is delta of n plus 2. Okay. Now, supposing I gave you a sequence, x of n is equal to 1, 0, 2, 0, 3, 0, 2, 0, 0, 1 and told you that the origin was here. Okay. One way to describe this signal, can be x of n. There is a unit sample function at time t equal to 0. So, basically you say there is delta of n that corresponds to. Okay. The next non-zero value is at time n equal to 2, but delayed in time. So, the scale factor is 2, the unit sample function is shifted by 2 units of time, delta of n minus 2. Then comes the next non-zero function, that is a sample value of 3, delta of n minus 4. Then again plus 2, delta of n minus 6. Where am I getting all these from? Just go ahead and write the index. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So basically this is the n index. Okay, and you can see which are the non-zero values. And then finally you get a sample of value 1. It's at position is equal to 9. That means that the unit sample function has to be delayed by 9 units of time, n minus 9. So you can represent it by means of a sketch. You can represent it by means of a sequence and you point where the 0 is occurring, or you can write it in terms of the scaled delta function, scaled and delayed delta function. Okay. An example would be, another example that would be useful for you to write down is to give me the expression for x of n. Okay, x of n would be equal to a of minus 3 is the scale factor, okay, delta of, it is corresponding to a position minus 3, it is advanced by 3 units of time. So, it will be delta of n plus 3. Then you have a1 which is at a position equal to n equal to 1. That means delta of n minus 1. This is a unit sample function that occurs at n equal to 1. Then you have a value a2 which is occurring at delta of n minus 2. Okay. Now, why did I not put a minus sign? Because a2 itself is negative. a2 is shown as a negative valued function. So, therefore, a2 is the value and the occurrence is at time n equal to 2. And finally, you have a 7 delta of n minus 7. Okay. So, any sequence which is of the form x of n, which is of the form x of 0, x of 1, x of 2 and so on onto the right side, x of minus 1, x of minus 2 and so on the left side, and this being the origin. You can show it as a sequence. You can also write it in a very compact form in the following way. You can say that it is a summation of these unit sample functions going from minus infinity to infinity, all these samples, and at every position you have a scale factor which corresponds to the sequence value x of k, and this occurs at a position delta n minus k, delta n minus k. So, I would like you to verify if this is correct. Where is x of 0 occurring? At delta of 0, okay, delta of n. Okay, delta of n, correct. Delta of n means it's non-zero at n equal to 0. Where is x of 1 occurring? X of 1 will occur at delta of n minus 1, correct. And similarly, x of minus 1 will occur at delta of n plus 1. Delta x of n x of minus 1, sorry. X of minus 1 occurs at delta of n plus 1. So, you can verify that this summation actually represents the sequence that you have at hand. So, this is x of n can be represented by means of the following expression, where this represents scaling, this represents the shifting in time, the position where it occurs, this represents the shifting, and of course, this is a summation. Okay. So, basically each of these terms in their summation is non-zero only at one position, where corresponding to that corresponding value of x of n. So, whatever value of x of n you take, n value of n equal to 2 or n equal to 10, one unit sample function will be non-zero, and the value of the scaling of the unit sample function will be corresponding to the value of the sequence. So this is a very useful representation of the sequence. Now, one of the things that one of the operations that we do on discrete time signals is an operation called time reversal. Time reversal. Okay, let us just look at a simple example. Supposing I have a sequence x of n, which is 0, 0, 0, 5, 4, 3, 2, 1, 0, 0, 0, and so on. Okay, and we are told that this is the 0 point. Okay, time reversal means y of n is equal to x of minus n. X of 0 remains, y of 0 is same as x of 0, but y of 1 is x of minus 1. Y of 2 is x of minus 2, and so on. So it is as if you took a mirror and then looked at the mirror image of it. So y of n has the following construction. Same position at 3. At n equal to 1, it's the same as minus 1. So this becomes 4, 5, then zeros. And on this side, you will have 2 and 1 and then zeros. Okay, so basically it's a mirror image. It is a reversal of the signal. Okay, I hope you are able to visualize it. So if x of n was a sequence that looked like this, okay, 5, 4, 3, 2, 1, and then zeros outside of that. If this was x of n, the corresponding time reverse signal y of n had had the values where this was the same as 3, this was 4, this was 5, and then you had 2 and you had 1 and then zeros. Okay, so 5, 4, 3, 2, 1. This is 5, 4, 3, 2, 1, and so on. Okay. What I would like you to do is to take this particular example and do the time reverse signal. Okay, let's do a quick check and look at the time reverse signal. Okay, so maybe easiest for us to write it as a sequence. P of n, write it as a sequence, 0, 0, then you have a of minus 3, then you have 0, 0, 0, you have a of 1, then you have a of 2, 4 zeros, and then we have a 7, and then subsequently all zeros. Okay, origin is right here. Okay, if I say y of n is equal to p of minus n time reverse signal, then it would be exactly rewriting it in the backward form. This would be 0, 0, 0, a of minus 3, 0, 0, and so on. Then you would have a1, a2, 4 zeros, and then you would have a7 and 0. So this would still be the origin. So basically you are reversing the sequence of the order. This is a time reversing operation. Again, it has a very useful role. We will look at it and study it in detail. What are some of the other operations that we can look at, other basic operations of discrete time signals? Some very interesting operations are there, basic operations, very useful for you to know what the notation is and also be able to capture it in terms of simple calculations using these operations. So supposing I had two discrete time sequences, x1 of n and x2 of n. the following basic operations can be defined. One is sequence addition. Sequence addition, also you can call it as signal addition. Two signals, you can in any way you can call that. Okay, so y1 of n will be equal to x1 of n plus x2 of n. Okay, so and this is for all n. You have to do this operation for all n. So, for example, if you wanted y1 of 0, it would be x1 of 0, the sample that was at time 0 for x1, added with the time of signal x2 of 0. And then y1 of 1 would be equal to x1 of 1 plus x2 of 1. Again, do it sample by sample at the same index that you are working with. Now, you can also have what is called a scalar addition. So, you have a scalar that is added to your sequence, scalar addition, and this is defined as y2 of n equal to alpha. Alpha is a scalar, it is a constant, added to your signal x2 of n. Again, this is for all values of n. y1 of 0 will be alpha plus x2 of 0. y1 of 1 will be equal to alpha plus x2 of 1, and so on. Okay, so you can just so that it's for all sequence values, the same value alpha gets added. This is a scalar addition. Then comes the two important things involving multiplication. So, one is sequence multiplication. Sequence multiplication. Okay, multiplication. So, y3 of n is equal to x1 of n multiplied with x2 of n. What do we mean? For every time index, you take the corresponding sample value of x1 and the sample value of x2 and multiply them together. Again, for all values of n, y1, y3 of 0, but this should be y2, not y2 of 0, y2, okay, this is y3. y3 of 0 will be equal to x1 of 0 multiplied with x2 of 0, okay, and so on. And the last one is scalar multiplication. Scalar multiplication, where you multiply the entire sequence with a value alpha multiplication. So, y4 of n, we give it as alpha times x1 of n. All the values of x are scaled by the corresponding value alpha. Okay. So, now I would like you to try out a quick example. So, this is an example which will help us just use the basic definitions. x1 of n is a sequence of 5 non-zero values. Okay, 1.5, 2, 3.4, -5 and 10. Okay, and the origin we must specify is at the sample where the value is equal to 2. That is a sample n. Then you have a second sequence, x2 of n equal to 2.2, 3, 2, 4.2 and 8. Again, just to make it a little bit interesting. Okay, so these. So we are then asked to obtain y1 of n, which is the addition of the two sequences, x1 of n plus x2 of n. y2 of n is equal to the product of the two sequences, x1 of n, x2 of n, okay, and then y3 of n is a product as a scaling of the two sequences. Okay, y3 of n is a scaling, so we call it as 3 by 2 n alpha n, and the last one will be an additive y4 of n equal to alpha plus x1 of n. Okay, I would like you to find out, I mean, basically, if let us say alpha equal to 2, you can then see what the corresponding values are going to be. So again, basic operations useful for us in terms of the various things that we can do with the signals.